Introduction to Encrypted ClientHello. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are exploring Encrypted ClientHello, commonly abbreviated as ECH, which is a critical privacy enhancement for TLS connections. Before we dive into the DNS aspects, it is important to understand what problem ECH solves. When you connect to a website using HTTPS, the TLS handshake begins with a ClientHello message from your browser to the server. Historically, this ClientHello message contained the server name indication, or SNI, in plaintext, revealing which specific website you are trying to visit, even though the actual content would be encrypted. This plaintext SNI creates a significant privacy vulnerability. Network observers, including internet service providers, corporate firewalls, or government censors, can see exactly which websites you're visiting by reading the SNI field. Even though they can't see what you're doing on those websites, the mere fact that you're connecting to a particular domain can be sensitive information. For instance, visiting a health information site, a political organization, or a news outlet in certain countries could put users at risk. Encrypted ClientHello solves this problem by encrypting the entire ClientHello message, including the SNI field, before it leaves your device. However, this creates a chicken and egg problem. How do you encrypt the ClientHello if you do not yet have a secure connection established? The answer involves using public key cryptography with keys distributed through DNS records. The DNS system publishes special records that contain the public keys needed to encrypt the ClientHello, allowing clients to encrypt their handshake before establishing the TLS connection. This presentation will explore how these DNS records work, what information they contain, how clients use them to encrypt the ClientHello, and the operational considerations for deploying ECH in production environments. We'll examine the HTTPS DNS record type, the ECH config structure, and the complete flow from DNS query to encrypted handshake. The privacy problem with SNI. To understand why encrypted ClientHello is necessary, we need to examine the server name indication mechanism and its privacy implications. SNI was introduced as an extension to TLS to solve a practical hosting problem. How can multiple websites with different domain names share the same IP address and still use HTTPS with valid certificates? When a web server hosts multiple domains on the same IP address, it needs to know which domain the client is requesting before it can present the correct TLS certificate. Without SNI, the server would have no way to know which certificate to send during the handshake. SNI solves this by having the client explicitly state the host name it is trying to reach in the ClientHello message, allowing the server to select and present the appropriate certificate. The problem is that SNI was designed when the primary concern was functionality, not privacy. The SNI field is sent in plaintext during the TLS handshake, before any encryption is established. This means anyone monitoring the network can read the SNI value and determine exactly which website you are visiting. The encryption only begins after the handshake completes, so while your actual data exchange is protected, the initial connection metadata is completely visible. This plain text SNI exposure enables various forms of surveillance and censorship. Network intermediaries can log which websites users visit, even if they cannot see the content. Countries can block access to specific websites by detecting their SNI values and dropping or redirecting those connections. Corporations can monitor employee browsing by examining SNI fields. Internet service providers can sell aggregated browsing data based on observed SNI values. Previous attempts to address this privacy issue, such as server name encryption or SNI encryption proposals, had various limitations. Encrypted ClientHello represents the current standardized approach, providing comprehensive protection by encrypting the entire ClientHello message rather than just the SNI field. This broader encryption also protects other potentially sensitive handshake parameters, including supported protocol versions, cipher suites, and TLS extensions. DNS HTTPS record type. The HTTPS DNS record type is a relatively new addition to the DNS protocol, defined in RFC 9460. This record type serves as a service binding and parameter specification mechanism, providing additional information about how to connect to HTTPS services. While it supports various connection parameters, its most important use case for our discussion is distributing encrypted ClientHello configuration. The HTTPS record type uses a numeric DNS record type value of 65, though it's typically referred to by its mnemonic name HTTPS in zone files and queries. This record type is fundamentally different from traditional DNS records like our AAA records that simply map names to IP addresses. Instead, HTTPS records provide structured service parameters that describe how clients should connect to a service. HTTPS records can contain multiple service parameters, each identified by a numeric key. These parameters include things like ALPN, which specifies supported application layer protocols, port, which indicates non-standard port numbers, IPv4 hint and IPv6 hint, which provide IP address hints for connection optimization, and most importantly for our purposes, ECH, which contains the encrypted ClientHello configuration. The HTTPS record exists at the same DNS name as the service you are trying to reach. For example, if you are connecting to example.com, you would query for an HTTPS record at example.com. This record tells your client not just the IP address to connect to, but also how to properly encrypt the ClientHello when establishing the TLS connection. The DNS response can include multiple HTTPS records with different priorities, allowing for failover and service redundancy. One important aspect of HTTPS records is that they are designed to work alongside traditional A and AAA records. A DNS zone can publish both types of records, with legacy clients using the A/AAA records, while modern clients capable of understanding HTTPS records get the enhanced connection information. This backward compatibility is crucial for incremental deployment of new technologies like encrypted ClientHello across the Internet. ECH config structure. The ECH config, which stands for Encrypted ClientHello Configuration, is a binary structure that contains all the information a client needs to encrypt its ClientHello message. This structure is distributed through the ECH parameter in HTTPS DNS records and contains cryptographic keys, protocol versions, and configuration options. At the top level, the ECH config structure begins with a version field that identifies which version of the encrypted ClientHello protocol is being used. The current standardized version is identified by the bytes, beginning with FE and ending with 0D, representing ECH draft version 13, which was adopted as the final standard. Different versions may have different structure formats or cryptographic requirements, so the version field is crucial for protocol negotiation. The most critical component of ECH config is the public key that clients will use to encrypt their ClientHello. This public key corresponds to a private key held by the server, creating an asymmetric encryption scheme. The public key is encoded using the format specified by the chosen key exchange algorithm, which is typically HPKE, the hybrid public key encryption scheme. HPKE combines elliptic curve Diffie-Hellman for key agreement with authenticated encryption for the actual message encryption. The ECH config also includes a maximum name length field, which specifies the longest name that can be encrypted in the ClientHello. This length limitation exists because the encrypted ClientHello needs to be a fixed size to avoid leaking information about the actual target hostname through length analysis. If your target hostname is shorter than the maximum, it will be padded to the specified length. Additionally, ECH config contains a public name field, also called the outer SNI. This is a domain name that will be sent in plaintext in the outer ClientHello, while the real target domain is encrypted in the inner ClientHello. The public name serves as a cover for the connection, allowing network observers to see that you are connecting to some general service, but not revealing the specific site you are actually accessing. Typically, the public name might be something generic, like the CDN provider's domain or the hosting provider's name, rather than the specific website. Querying for HTTPS records. To retrieve encrypted ClientHello configuration, clients perform DNS queries for HTTPS records using standard DNS resolution mechanisms. The query process is straightforward but requires support for the HTTPS record type in both the client resolver and the DNS infrastructure. A client queries for the HTTPS record type at the target domain name using a standard DNS query. For example, to connect to www.example.com, the client would send a DNS query asking for HTTPS records at that exact name. The query uses the standard DNS query format with the query type set to 65, which is the numeric ID for HTTPS records. This query can be sent over traditional UDP port 53, over TCP for larger responses, or increasingly over encrypted DNS protocols like DNS over HTTPS or DNS over TLS. The DNS response will contain one or more HTTPS records if the domain supports encrypted ClientHello. Each HTTPS record includes a priority value, with lower numbers indicating higher priority. The client should attempt to use the highest priority record first, falling back to lower priority records if the connection fails. This priority mechanism enables servers to specify preferred connection methods while maintaining fallback options. Within each HTTPS record, the ECH parameter contains the ECH config structure encoded in base 64 format in zone files, or as raw binary in DNS wire format. The client extracts this binary ECH config structure and parses it to obtain the public key and other configuration parameters needed for encrypting the ClientHello. If multiple HTTPS records contain ECH parameters, the client typically uses the highest priority one that it supports. DNS caching plays an important role in the efficiency of this system. HTTPS records have time-to-live values just like other DNS records, and resolvers will cache them for the specified duration. This means clients do not need to query for the ECH config on every connection. They can reuse cached values until they expire. However, this caching also means that servers need to coordinate DNS record updates with key rotation schedules to avoid clients using outdated ECH config values. HPKE encryption scheme. Hybrid public key encryption, or HPKE, is the cryptographic scheme used to encrypt the ClientHello message. HPKE is defined in RFC 9180 and provides a modern, standardized approach to public key encryption that combines the best properties of different cryptographic primitives. HPKE operates in three conceptual phases: key agreement, key derivation, and authenticated encryption. The key agreement phase uses elliptic curve Diffie-Hellman to establish a shared secret between the client and server. The client generates an ephemeral key pair, uses the server's public key from the ECH config, and performs an ECDH operation to derive a shared secret that only the client and server can compute. The key derivation phase takes that shared secret and uses a key derivation function, typically HKDF, which stands for HMAC-based key derivation function, to derive the actual encryption keys. HKDF expands the shared secret into multiple keys for different purposes: encryption keys, authentication keys, and nonces. This derivation includes context information, like the protocol version and configuration details, binding the derived keys to the specific ECH context. The authenticated encryption phase uses an AEAD cipher. AEAD stands for Authenticated Encryption with Associated Data. This cipher is used to encrypt the ClientHello content. Common AEAD choices include AES-GCM or ChaCha 20 Poly 1305. The AEAD cipher not only encrypts the client hello message to provide confidentiality, but also computes an authentication tag. This tag proves the message has not been tampered with. This authentication is crucial. It prevents network attackers from modifying the encrypted client hello in transit. HPKE provides several important security properties for ECH. It ensures that only the intended server can decrypt the client hello, since only the server possesses the private key corresponding to the public key in the ECH config. It provides forward secrecy because the client generates an ephemeral key pair for each connection, meaning compromise of the server's long-term key does not allow decryption of past client hellos. And it provides integrity protection through the AEAD authentication, ensuring that tampering can be detected. Inner and outer client hello. Encrypted client hello creates a two-layer structure with an inner client hello and an outer client hello. Understanding the distinction between these two messages is essential for grasping how ECH maintains both privacy and functionality. The inner client hello is the actual, complete client hello message that contains all the real connection parameters the client wants to use. This includes the true server name indication showing the actual website being accessed, the full list of supported cipher suites, all TLS extensions the client wants to use, and any other handshake parameters. This inner client hello is encrypted using HPKE with the public key from the ECH config, making it unreadable to network observers. The outer client hello is a specially crafted client hello that is sent in plaintext and contains the encrypted inner client hello as one of its extensions. The outer client hello contains a fake or generic server name indication, typically matching the public name from the ECH config. This outer SNI serves as a decoy, showing network observers a plausible but non-specific connection target. For example, the outer SNI might show a generic CDN domain like cloudflare.com, while the encrypted inner SNI contains the real target like sensitivehealthsite.com. The outer client hello must contain enough information to at least route to the correct server that holds the ECH private key. This means it typically includes real IP addressing information and basic TLS parameters, but strategically obscures or generalizes sensitive fields. The outer client hello's cipher suite list might be a subset of the inner client hello's list, containing only the most common options to avoid fingerprinting while ensuring compatibility. When the server receives this two-layer structure, it first examines the outer client hello and recognizes the encrypted client hello extension. It then uses its private key to decrypt the inner client hello and processes that inner message as the authoritative handshake request. If decryption succeeds, the server continues the handshake based on the inner client hello's parameters. If decryption fails, perhaps due to using an old ECH config, the server may fall back to processing the outer client hello or rejecting the connection entirely. This two-layer approach elegantly solves the chicken and egg problem of encrypting connection metadata. The outer client hello provides just enough information for routing and compatibility, while the inner client hello carries all the sensitive details in encrypted form. Network observers see only the generic outer client hello, learning nothing about the true connection target. ECH configuration distribution. Distributing ECH config structures through DNS requires careful coordination between DNS infrastructure and web servers. The configuration must be published, maintained, and synchronized to ensure clients can always obtain current, valid encryption keys. Servers generate ECH config structures as part of their ECH setup process. This involves generating a public-private key pair, typically using one of the HPKE key agreement algorithms like X25519 or P256 elliptic curves. The server retains the private key securely, never exposing it outside the server environment. The public key is packaged into an ECH config structure along with the chosen parameters, version information, maximum name length, and public name. The server then exports this ECH config structure in a format suitable for DNS publication. The binary ECH config is encoded, typically in base 64, for human-readable zone files, and formatted as the value of the ECH parameter in an HTTPS DNS record. The zone file entry might look something like example.com in https 1.ech equal operator base 64 encoded config. The priority value, shown as 1 in this example, determines the preference order if multiple HTTPS records exist. DNS zone administrators add these HTTPS records to their authoritative DNS servers. This means your DNS infrastructure needs to support the HTTPS record type. For older DNS server implementations, this might require software updates. These records are published with appropriate TTL values. These values balance the trade-off between caching efficiency and how often keys can be rotated. Shorter TTLs allow for faster key rotation, but they increase the DNS query load. Conversely, longer TTLs reduce query traffic but slow down security updates. Coordination between the web server and DNS is critical during key rotation. When a server wants to rotate its ECH keys, it must publish the new ECH config to DNS while continuing to accept connections encrypted with the old key until all cached DNS records expire. This overlap period ensures that clients using cached ECH config values can still connect successfully. A typical rotation process involves publishing the new key to DNS, waiting for the TTL period to elapse, then finally retiring the old private key once no clients should be using it anymore. Some deployment architectures use multiple HTTPS records with different ECH config values to enable zero downtime key rotation. The DNS zone publishes both old and new configurations simultaneously with the same priority, allowing clients to use either. After the transition period, the old configuration is removed from DNS. This multi-key approach provides additional resilience against DNS caching issues and clock skew. Client connection flow with ECH. When a client establishes a connection using encrypted ClientHello, it follows a multi-step process that integrates DNS resolution, cryptographic operations, and TLS handshake procedures. Understanding this complete flow shows how all the components work together. The process begins when a user enters a URL or a client application needs to establish an HTTPS connection. The first step is DNS resolution. The client queries for HTTPS records at the target domain name, in addition to or instead of traditional A and AAA records. Modern resolvers might perform these queries in parallel to minimize latency. The DNS response returns HTTPS records containing the ECH parameter with the ECH config structure. Upon receiving the ECH config, the client parses the binary structure to extract the server's public key, the supported HPKE cipher suites, the maximum name length, and the public name. The client verifies that it supports the ECH config version and at least one of the specified HPKE cipher suites. If the client cannot support any of the offered configurations, it may fall back to a connection without ECH. This fallback behavior, however, is configurable based on policy. The client then constructs two ClientHello messages. First, the inner ClientHello, which contains all real connection parameters, including the true SNI. Second, the outer ClientHello, which contains the public name as its SNI. The client uses HPKE to encrypt the inner ClientHello with the server's public key from the ECH config. This encryption produces both the encrypted payload and an encapsulated key, which is the client's ephemeral public key needed for the server to decrypt the message. The client embeds the encrypted inner ClientHello and the encapsulated key into the encrypted _client_hello extension of the outer ClientHello. This outer ClientHello is then sent to the server over the TCP connection established to the IP address obtained from DNS. The outer client hello travels through the network in plaintext, visible to all intermediaries, but the encrypted inner client hello remains confidential. The server receives the outer client hello, recognizes the encrypted _client _hello extension, and uses its private key to decrypt the inner client hello. If decryption succeeds, the server processes the inner client hello as the authoritative handshake message, selecting cipher suites, generating its server hello response, and continuing the TLS handshake based on the inner parameters. The rest of the TLS handshake proceeds normally, with all subsequent messages encrypted under the negotiated TLS keys. From the client's perspective, if everything works correctly, the use of ECH is transparent beyond the initial setup. ECH retry mechanisms. Despite careful configuration, ECH connections can fail for various reasons. Stale ECH config values cached in DNS, server key rotation during connection attempts, network interference, or misconfiguration. The ECH specification includes retry mechanisms to handle these failures gracefully and provide fallback options. When a server cannot decrypt the inner client hello, perhaps because the client used an outdated ECH config with an old public key, the server has two primary options. The server can reject the connection entirely with a specific TLS alert, indicating ECH was required but failed. Alternatively, and more commonly, the server can send a retry configs response that contains one or more current ECH config structures that the client should use for retry attempts. The retry configs mechanism allows the server to provide updated configuration without requiring the client to perform another DNS query. When the server sends retry configs in its handshake rejection, it includes fresh ECH config structures in the server hello message. The client receives these configurations, stores them, and immediately attempts a new connection using the updated ECH config. This rapid retry minimizes user visible latency compared to waiting for DNS cache expiration. Clients implement retry logic with safeguards to prevent infinite loops or retry storms. Typically, a client will retry once with server-provided configurations, but will not repeatedly retry if the server keeps sending different retry configurations. This prevents malicious or misconfigured servers from trapping clients in retry loops. After a failed retry attempt, the client may fall back to a connection without ECH if allowed by policy, though strict ECH policies might treat this as a connection failure, rather than silently downgrading security. The retry mechanism also serves a security purpose by allowing servers to validate client capabilities. A server might intentionally reject initial ECH attempts and provide retry configs to ensure the client properly implements the retry logic. This helps detect and mitigate certain downgrade attacks where a network adversary might try to strip ECH support by tampering with DNS responses or client hello messages. A client that properly retries demonstrates it received and processed the server's retry configs, increasing confidence in the connection's security properties. CDN and hosting provider support. Content delivery networks and hosting providers play a crucial role in ECH deployment because they often terminate TLS connections on behalf of many customer websites. When a CDN or hosting provider implements ECH, they must manage ECH config distribution and private key infrastructure for potentially millions of domains simultaneously. CDN providers typically implement ECH at their edge servers, which are the TLS termination points for customer traffic. Each edge server needs access to the ECH private keys for all domains it serves. This creates a key management challenge at scale, as keys must be securely distributed to thousands of edge locations worldwide while maintaining the ability to rotate keys regularly for security purposes. The architectural approach often involves generating ECH config structures centrally and distributing them along with the private keys to edge servers through secure channels. Some CDNs use hardware security modules or secure enclaves to protect private keys at the edge. The ECH config public keys are then published through the CDN's DNS infrastructure, which may be the customer's authoritative DNS or a DNS service managed by the CDN itself. For shared hosting environments where multiple customer domains share the same IP address, ECH provides particular benefits. The public name in the ECH config can be set to a generic hosting provider domain, so network observers see connections to the hosting provider but cannot determine which specific customer site is being accessed. This protects customer privacy while maintaining the hosting provider's business model of shared infrastructure. CDN providers must also handle the complexity of serving both ECH-enabled and legacy clients simultaneously. This requires maintaining parallel configurations where legacy clients receive traditional TLS handshakes while modern clients use encrypted ClientHello. The edge infrastructure needs to detect ECH support and incoming connections and route them appropriately, while also managing fallback scenarios when ECH negotiation fails. CDN and hosting provider support. Content delivery networks and split mode ECH architecture. Split mode ECH represents an advanced deployment architecture where the server that terminates TLS and holds the ECH private key is different from the servers that actually host the target websites. This architecture is particularly important for large-scale deployments and CDN scenarios where separation of concerns provides operational flexibility. In split-mode architecture, a front-end server receives the encrypted ClientHello, decrypts it using the ECH private key, and then forwards the decrypted information to back-end origin servers. The front-end server essentially acts as an ECH gateway, handling the privacy-sensitive decryption while back-end servers remain focused on application logic. This separation allows organizations to centralize ECH key management while distributing application hosting across many servers. The communication between front-end and back-end servers in split-mode deployments typically occurs over an internal network or through secure tunnels. The front-end server extracts the true SNI from the decrypted inner ClientHello and uses it to route the connection to the appropriate back-end server or virtual host. This routing decision happens after ECH decryption but before completing the TLS handshake with the client. Split mode introduces additional complexity in certificate management. The front-end server needs certificates for the public name that appears in the outer ClientHello, while back-end servers need certificates for the actual target domains in the inner ClientHello. The handshake must seamlessly transition from the front-end certificate to the back-end certificate, or the front-end must be able to present certificates on behalf of all back-end domains. One implementation approach uses TLS proxying where the front-end server completes one TLS handshake with the client and then establishes a separate TLS connection to the back-end. Alternatively, the front-end can use TLS session resumption or early data mechanisms to efficiently forward the decrypted handshake information to backends. The choice depends on performance requirements, complexity tolerance, and security boundaries within the infrastructure. ECH and DNS privacy protocols. The security benefits of encrypted ClientHello can be undermined if DNS queries themselves leak the target domain information. When a client queries for HTTPS records to obtain ECH config, that DNS query reveals which domain the client intends to connect to, potentially negating the privacy gains from ECH. This makes DNS privacy protocols essential companions to ECH deployment. DNS over HTTPS, or DOH, encrypts DNS queries by tunneling them through HTTPS connections to DNS resolvers. When a client uses DOH to query for HTTPS records containing ECH config, the DNS query itself is encrypted and authenticated, preventing network observers from seeing which domain's ECH configuration is being requested. DOH operates over port 443, making it indistinguishable from regular HTTPS traffic to network intermediaries. DNS over TLS, or DOT, similarly encrypts DNS queries but uses a dedicated port 853 and establishes a TLS connection specifically for DNS traffic. DOT provides the same privacy protections as DOH, encrypting both the queries and responses, but the use of a dedicated port makes it easier for network administrators to identify and potentially block DNS over TLS traffic. Both DOH and DOT prevent DNS query snooping and tampering. The combination of ECH with encrypted DNS creates comprehensive connection privacy. The DNS query for ECH config is encrypted through DOH or DOT, preventing observers from learning which domain's ECH configuration is being requested. Then the TLS handshake uses ECH to encrypt the ClientHello, preventing observers from learning the actual connection target. This dual layer of encryption protects both the DNS lookup phase and the connection establishment phase. However, this privacy protection chain has some limitations. The client still needs to establish an encrypted DNS connection to a trusted resolver, and that initial bootstrap connection might reveal information. Additionally, IP address-based tracking remains possible since the client must connect to the IP address of the target server, which might be associated with specific services. Techniques like IP address rotation, anycast addressing, and shared hosting help mitigate but don't completely eliminate these vectors. Monitoring and observability. Deploying encrypted ClientHello introduces new challenges for network monitoring and observability. Traditional network monitoring tools that rely on inspecting plaintext SNI fields to track application performance, detect anomalies, or generate usage statistics need to be updated or replaced when ECH is deployed. Server-side logging becomes more important with ECH because the server is the only entity that can decrypt and observe the true ClientHello contents. Servers need to log the real SNI from the inner ClientHello for operational purposes like performance monitoring, debugging, and capacity planning. However, these logs become more sensitive since they're the only authoritative source of which specific sites clients are accessing. Monitoring systems need to distinguish between different types of connection failures. With ECH, a failure might occur because the client used a stale ECH config, because the server's private key wasn't available, because network middleboxes interfered with the encrypted extension, or because of genuine TLS handshake failures unrelated to ECH. Proper error categorization and metric collection help operators understand ECH deployment health. Performance monitoring must adapt to measure ECH-specific metrics. Important measurements include the ECH success rate, which tracks what percentage of ECH attempts succeed versus falling back to plaintext. Retry rate, measuring how often clients need to use retry configs. And decryption latency, tracking the computational overhead of HPKE decryption on server performance. These metrics help operators tune their ECH deployment and identify issues. Network operators lose some visibility into application layer traffic patterns with ECH deployment. Middleboxes, such as firewalls or intrusion detection systems, that previously used SNI for traffic classification or policy enforcement, now require alternative approaches. Some organizations implement server-side reporting mechanisms where backend servers securely report traffic patterns to central monitoring systems. Alternatively, they might use encrypted telemetry protocols that preserve privacy while enabling necessary operational visibility. ECH client implementation considerations. Client software implementing encrypted ClientHello faces several design decisions and technical challenges. Browser vendors, operating system providers, and application developers must carefully implement ECH to balance privacy benefits with compatibility, performance, and user experience. One key decision is the fallback policy when ECH is unavailable or fails. Strict mode means the client will refuse to connect if ECH cannot be negotiated, providing maximum privacy protection but potentially breaking connectivity to misconfigured or non-supporting servers. Opportunistic mode means the client attempts ECH but falls back to plaintext ClientHello if necessary, maintaining compatibility but providing weaker privacy guarantees. Different applications may choose different policies based on their security requirements. Client implementations must handle ECH config caching effectively. Since ECH config structures are obtained from DNS queries, clients typically cache them alongside DNS responses. The cache implementation needs to respect DNS TTL values but also handle scenarios where cached configs become invalid due to server-side key rotation. Clients should implement appropriate retry logic and cache eviction strategies to balance performance with freshness. The client must also implement the HPKE cryptographic operations correctly and efficiently. HPKE encryption adds computational overhead to connection establishment, so clients need optimized implementations of elliptic curve operations and AEAD ciphers. Some platforms can leverage hardware acceleration for these operations, while others need carefully tuned software implementations to avoid introducing noticeable latency in connection establishment. User interface considerations are subtle but important. Most users do not need to know about ECH, so the client should transparently enable it when available. However, privacy-conscious users might want visibility into whether their connections are ECH protected. Browser developer tools and connection information dialogues might expose ECH status for technical users. Error messages when ECH fails need to be clear enough for technical diagnosis while not alarming non-technical users. ECH and certificate transparency. Certificate transparency is a system that publicly logs TLS certificates to detect misissuance and improve the web PKI security. The interaction between certificate transparency and encrypted ClientHello raises interesting operational and privacy considerations, particularly around certificate logging and domain enumeration. When a server presents a certificate during the TLS handshake, that certificate typically includes signed certificate timestamps, or SCTs, which are promises from certificate transparency logs that the certificate has been or will be logged. These certificates contain the domain names they are valid for in the subject alternative name field. Even though ECH encrypts the SNI, the certificate presented during the handshake reveals which domains the server supports. This creates a potential privacy leak. An attacker monitoring the network sees the outer client hello with a generic public _name, but then sees the server's certificate containing the real domain names. While this does not definitively prove which specific domain the client requested, it narrows down the possibilities significantly if the server only hosts a few domains. This is particularly problematic for servers that use unique certificates per domain. One mitigation is using wildcard certificates or certificates that cover many domains through subject alternative names. A server hosting example.com could use a certificate that is also valid for many other domains or for a wildcard like star.cdnprovider.com. This makes certificate observation less informative about which specific domain was requested. However, this approach has limits because browsers and security policies often restrict wildcard certificate usage. Another approach involves the server presenting different certificates based on the connection context. In split-mode architectures, the front-end server might present a generic certificate initially, with the actual domain-specific certificate only presented after additional protocol negotiation. Some proposals suggest encrypted certificate messages where even the server's certificate is encrypted, though this adds significant complexity to the TLS protocol and certificate transparency integration. The fundamental tension is that certificate transparency requires public logging of certificates, which inherently reveals domain information, while ECH tries to hide domain information from network observers. Long-term solutions might involve privacy-preserving transparency mechanisms or architectural changes that separate domain validation from certificate presentation, but these remain active areas of research and standardization. Performance impact and optimization. Encrypted ClientHello introduces computational and latency overhead that needs to be carefully managed for acceptable performance. Understanding the performance impact and optimization strategies helps operators deploy ECH without degrading user experience. The primary computational overhead comes from HPKE operations. The client must perform an elliptic curve scalar multiplication for the key agreement, run HKDF for key derivation, and execute an AEAD encryption. Modern processors with hardware support for AES and polynomial multiplication can optimize these operations significantly, but older devices or software-only implementations may experience measurable latency increases, typically in the range of 1 to 5 milliseconds per connection. Network latency impact comes from the additional DNS query for HTTPS records. If the client does not already have the ECH config cached, it needs to perform an extra DNS lookup before establishing the TLS connection. This DNS query adds a round-trip time to connection establishment. However, this overhead is mitigated by DNS caching, parallel DNS queries for /quad A and HTTPS records, and DNS prefetching where browsers proactively resolve DNS records for likely future connections. Server-side decryption adds CPU load that is proportional to the connection rate. Busy servers handling thousands of connections per second must decrypt thousands of inner client hellos per second. Using HPKE, this requires adequate CPU resources and may benefit from hardware acceleration. Some server implementations optimize by using connection pools or session resumption to amortize the ECH overhead across multiple requests within the same session. Message size increases slightly with ECH because the outer client hello must contain both the encrypted inner client hello and additional framing. The encrypted payload is larger than the plaintext would have been due to EAD authentication tags and HPKE encapsulated keys. Typical overhead is 100 to 200 bytes, which is generally acceptable but can matter for connection establishment over high latency or bandwidth-constrained links. Optimization strategies include connection reuse through HTTP/2 or HTTP/3, where the ECH overhead is amortized across many requests within a single connection. Early data mechanisms in TLS 1.3 allow sending application data in the first round trip, overlapping application-level latency with handshake latency. Client implementations can also prefetch ECH config values during idle time, and servers can use connection coalescing to handle multiple domains over a single TLS connection. Security analysis and threat model. Analyzing the security properties of encrypted ClientHello requires understanding both what it protects against and what threats remain outside its scope. A clear threat model helps operators set appropriate expectations and implement complementary security measures. ECH primarily protects against passive network observation of the TLS handshake. An attacker who can see network traffic in transit cannot determine which specific domain the client is connecting to, because the true SNI is encrypted in the inner client hello. The outer client hello reveals only the generic public name, which might indicate the CDN or hosting provider, but not the specific customer site. This protection extends to other client hello parameters that might reveal information about the connection intent. Active network attacks are partially mitigated by ECH. An attacker who modifies network traffic might try to strip the encrypted client hello extension, or tamper with the encrypted payload. However, HPKE's authenticated encryption prevents undetected tampering with the encrypted inner client hello. If an attacker removes the ECH extension entirely, the server will only see the outer client hello, which should contain a generic SNI rather than the real target. The server may then reject these connections based on policy. Traffic analysis attacks remain possible despite ECH. An attacker observing encrypted traffic can still infer information from IP addresses, connection timing, packet sizes, and traffic patterns. If a particular IP address hosts only one website, connecting to that IP reveals the destination regardless of SNI encryption. Similarly, traffic analysis might identify specific websites based on characteristic request patterns, even though the handshake is encrypted. ECH doesn't claim to prevent these attacks. It only addresses handshake privacy. Server compromise represents a critical threat boundary. If an attacker compromises the server and obtains the ECH private key, they can decrypt past and future inner client hellos, provided they can capture the network traffic. This is why ECH private keys should be rotated regularly and protected with strong access controls. Forward secrecy properties mean that compromising the ECH key does not allow decryption of the actual TLS session after the handshake completes. It only decrypts the client hello itself. DNS security remains crucial. If an attacker can tamper with DNS responses, they might be able to substitute malicious ECH config values containing attacker-controlled public keys. This would allow the attacker to decrypt inner client hellos. DNSSEC signatures on HTTPS records provide authentication, and encrypted DNS protocols prevent DNS tampering in transit, but the DNS resolver itself must be trusted. The entire ECH security model ultimately relies on the integrity of the ECH config distribution mechanism. Deployment status and ecosystem adoption. The deployment of encrypted ClientHello across the Internet ecosystem is progressing but remains incomplete, with various stakeholders at different stages of implementation and adoption. Understanding the current deployment landscape helps set realistic expectations for when ECH will provide meaningful privacy protection at scale. Major browser vendors have been at the forefront of ECH implementation. Firefox enabled ECH support by default for users who use DNS over HTTPS, providing automatic privacy protection when connecting to ECH-enabled servers. Chrome has implemented ECH support and is rolling it out gradually, with the feature available in recent versions but not yet enabled by default for all users. Safari has implemented ECH in recent versions with similar gradual rollout strategies. These browser implementations drive client-side adoption and create demand for server-side support. Content delivery networks and hosting providers are critical for server-side ECH adoption. Cloudflare was an early adopter, enabling ECH across their network and providing it automatically to customer domains. Fastly and other CDN providers have announced ECH support with varying deployment timelines. These CDN deployments are particularly impactful because they provide ECH to millions of websites simultaneously without requiring individual site operators to implement anything. Origin server implementations in popular web servers are progressing. Nginx has experimental ECH support via patches and third-party modules. Apache HTTP Server has ongoing development efforts. Specialized TLS termination proxies, like Envoy and HA Proxy, are adding ECH capabilities. However, adoption in these projects tends to lag behind browser and CDN implementations, and many production deployments do not yet use versions with ECH support. DNS infrastructure must support HTTPS records for effective ECH deployment. Major DNS hosting providers, including Cloudflare DNS, Google Cloud DNS, and AWS Route 53, all support HTTPS records, allowing operators to publish ECH config values. However, many legacy DNS hosting platforms do not yet support this record type, creating deployment friction for websites that want to enable ECH DNSSEC support, while important for ECH security, remains inconsistently deployed across DNS infrastructure. The current state means that ECH provides privacy protection for some fraction of web traffic, but far from universal coverage. Users running modern browsers with ECH enabled will get protection when connecting to ECH supporting websites, but will fall back to plaintext SNI for other sites. As adoption increases across browsers, CDNs, and origin servers, the privacy benefits will expand, but complete internet-wide deployment remains years away. Operators should view ECH as part of a long-term privacy enhancement rather than an immediate universal solution. Future directions and ongoing development. Encrypted ClientHello represents current best practice for TLS handshake privacy, but research and standardization continue to address limitations and explore enhancements. Understanding ongoing development efforts helps anticipate future changes and improvements to the ECH ecosystem. One active area is improving certificate privacy to complement ClientHello encryption. As discussed earlier, the server certificate can leak domain information even when ECH successfully encrypts. The SNI proposals for encrypted server certificates or certificate compression aim to address this leak. Some designs suggest encrypting the certificate message using keys derived during the ECH decryption, while others explore using compressed certificate references that do not contain full domain names. GREASE for ECH, which stands for Generate Random Extensions and Sustain Extensibility, is a mechanism to prevent ossification of the ECH ecosystem. GREASE involves clients occasionally sending fake encrypted ClientHello extensions even when not actually using ECH, or sending ECH attempts for servers that do not support it. This ensures that network middleboxes and servers do not come to depend on the absence of ECH, making future deployment easier. GREASE strategies for ECH are being refined based on deployment experience. Alternative key distribution mechanisms beyond DNS are being explored. While HTTPS records work well, they tie ECH deployment to DNS infrastructure and create dependencies on DNS resolver trust. Some proposals investigate using HTTP alternative services, ACME protocol extensions, or out-of-band key distribution through browser trust stores or operating system updates. These alternatives might provide more flexible deployment models or stronger security properties in certain scenarios. Integration with other privacy-enhancing technologies is an ongoing focus. Combining ECH with IP address privacy mechanisms like mask proxying or Apple's Private Relay creates more comprehensive connection privacy. Research explores optimal architectures for combining these technologies, understanding their performance trade-offs, and developing standardized integration patterns that allow privacy technologies to compose effectively. Post-quantum cryptography migration is a looming consideration. Current ECH implementations use elliptic curve cryptography for HPKE key agreement, which is vulnerable to future quantum computers. As post-quantum TLS becomes a reality, ECH will need to support post-quantum HPKE variants using lattice-based or other quantum-resistant algorithms. This migration needs careful planning to avoid doubling the size of ClientHellos and maintaining performance with less efficient post-quantum primitives. Thank you for your attendance. Please consider subscribing to the channel.